In this video, we'll talk through the thermodynamic differences between reversible and irreversible processes. We'll also practice quantifying the work done by reversible isothermal expansion of an ideal gas. Ever try to unboil a boiled egg, unrust a rusty nail, or unburn burnt toast? Probably not with much success, because these are all examples of irreversible processes. In thermodynamics, all processes can be categorized as either reversible or irreversible. The difference relates to how a system changes from one state to another. Irreversible processes, as the name suggests, can't be reversed. You try to cool a boiled egg, but the system and its surroundings can't be returned to its original state. The opposite is a reversible process. A classic example is water changing state to ice. Reversible processes occur through a series of intermediate equilibrium states. The system is at equilibrium at each step of the process. The change can be reversed, and everything will be exactly as it was, with no trace left on either the system or its surroundings. Which do you think happens more quickly, reversible or irreversible processes? Irreversible processes occur spontaneously, or at a finite rate. They don't follow equilibrium conditions, so they happen more quickly. This is why calculating irreversible changes, thermodynamic quantities, is more difficult. We can measure the state before and after the change, but not the infinitesimally small state changes that happen in between. Since reversible changes keep the system at equilibrium, they can be plotted by a continuous line on an indicator diagram. To model the principles of thermodynamics, we can think of an ideal gas in a vessel with a movable piston. The gas is held at a constant temperature. As the piston is pushed, it absorbs heat and converts that energy to do work. This is called an isothermal reversible expansion. The formula for the work done by the ideal gas when the external conditions are constant is minus n RT times by the natural logarithm of Vt over Vi. Here n is the number of moles of the gas, R is the universal gas constant, T is the temperature of the gas, V is the initial volume of the gas, and Vf is the final volume of the gas. Say 2 moles of ideal gas undergo isothermal reversible expansion at 300 Kelvin. The gas expands from 1 litre to 2 litres. How much work has been done? Pause the video now if you want to try and work out the answer on your own. Write the expression for the work done by the gas during an isothermal reversible expansion. Substitute the values for N, R, T, Vi and Vf in the above formula and solve for the work done. The answer is approximately 3,485 joules of work done. Here, the negative sign indicates work done by the gas during the expansion. We have learned the difference between reversible and irreversible changes and how to calculate the work done by an ideal gas undergoing isothermal reversible expansion. Thanks for watching. If you enjoyed this video, like and subscribe for plenty more like it.